Okay, our next third speaker of second day is Andrzej Grzesik from Jagiellonian, Krakow. He will be telling us something about cycles of given length in oriented graphs.
Thank you very much, Frank, for the invitation and announcing my talk. I hope you can hear me well. Perfect. I'm glad to be at least virtually in Korea. Maybe next time I will be able to see you in person. It's always good to see you, even like this. Yes, I want to talk about two results, which are, one is based on a joint work with Dan Kral, Laci Lovas, the junior one, and Jan Wolec, while the other one is together with students Justyna Jaworska, Bartley Kielak, and Tomek Ślusarczyk. Yes, and my main topic is maximizing cycles of a particular length in oriented graphs. So let me start with the easiest question. What's the maximum number of directed triangles in an n-vertex oriented graph? You can easily see that if I have two vertices not connected by edge at all, it's not helping. So I can assume basically that my graph is a tournament. Similarly to what Alex was doing yesterday. So what's the maximum number of triangles? On every talk, there should be at least one proof. So let me prove this thing. If I want to calculate the number of directed triangles, I can just calculate the number of all pairs and remove transitive triangles. Yep, and the number of transitive triangles, it's exactly number of edges in out neighborhood of a vertex. If I concentrate on a particular vertex, then exactly transitive triangle sitting on this vertex is size of its neighborhood over 2. Yes, so in other words, I have this equality. And now using convexity, I can just prove that this is at most this value. And this is exactly n times n squared minus 1 over 24. Yeah, when you look at the inequality here, you'll clearly see that this can be achieved for any odd integer n in any regular tournament. The only thing I require, the degree of every vertex is exactly n minus 1 over 2. For even tournaments, I mean on even number of vertices, this can be also proved with a slight different bound, and both proofs were done already in 40s. So this is well known and easy to count, as you can see. When we move to 4 cycles, then a similar reasoning, but for pairs and some different convexity argument can be shown, can be used to show that the bound on the number of C4s is the following, as we can see here. So there are some divisibility issue and some constant which are not really interesting. So let me normalize it to see better what's going on. I will be using the same as it was done in previous papers on the topic. So instead of maximum number of cycles, I will be counting maximum number of cycles divided by the expected number in a random tournament. Yeah, we know what's the expected number of cycles of length L in a random tournament. If I divide it and go to the limit, then I get basically the main term. I'm forgetting about this -1, -3, and those trashes just to see what's the main term. Okay, so this is my C of L, this maximum number of cycles normalized by the random tournament. Okay, so in particular, the results I already mentioned are showing that for triangles, the maximum is 1, because as it's achieved in any regular tournament, also in a random tournament, so the maximum is exactly the same as in the random tournament, while for 4 cycles, this computation shows that this is above 1, it's 4 over 3. So what happened later? Recently, 5 years ago, Komarov and Mackey they show that for 5 cycles, also quasi-random tournament is maximizing number of 5 cycles in the limit, while for C6 and C7, the same happening, but whenever length of the cycle is divisible by 4, in particular for C8, it's not 1 anymore, it's something strictly bigger. Yeah, so we can see that for C4, it was something bigger, and for divisible by 4, in general, we have a construction, which is giving something better than the random one. And because of this, the following conjecture appeared. So if I take any length, of course, at least 3, which is not divisible by 4, then the maximum number of cycles is basically the same as in a quasi-random tournament. And so you cannot do anything better than in a random tournament. So what's happening for L divisible by 4? The second conjecture is saying that this is this number, some ugly summation. So we can express it using Riemann zeta function. Basically, the idea is that this is quickly tending to 1. So it's something like 1 plus 2 over pi to the power of L. Okay, why this ugly function? So it comes from the construction, and the construction is following. It's called a carousel tournament. We put all the vertices on a cycle and then connect every particular vertex with forward edges to everything that is in the first half and from everything that it's in the second half. Yeah, and now imagine that you rotate this over whole circle and you get a tournament. Yeah, so every vertex has a forward edge to everything that is forward up to half of the circle. Okay, this way we construct the so-called carousel tournament, and it gives this number of cycles of length L. It looks ugly, but it comes from the fact that you can sometimes not just go around, finish a cycle, but go a few times around. And this way we get some ugly integration. And that's why the expression is not so nice. Okay. So what was proven earlier, Bartley and they proved that the first conjecture, so for L not divisible by 4, holds if we additionally assume that our tournaments are regular. This way it's far easier, and it was able to prove. Okay, but in general, it was not known except those special values they presented in the previous slide. And recently, we've done Lazzi and Diane, we proved the first conjecture completely. So if you want to maximize cycles not divisible by 4, then you cannot do in the limit better than in the random tournament. For the cycles divisible by 4, we managed to prove an upper bound, which is asymptotically the same order. I mean, asymptotically in terms of L. So in other words, you see that here is 1 plus 2 times 2 over pi to the power of L times some constant, which is tending to 1. And here we prove also 1 plus 2 over pi to L with some epsilon. And this holds for L large enough. For the first open case, which is 8th cycle, we managed to prove the exact bound, and this is exactly the number coming from the carousel tournament. So what we are saying is that we strongly believe that the conjecture is true. So really the carousel tournament is maximizing, and we see that you cannot do anything better asymptotically. And for 8 cycles, it matches the construction, the same as for 4 cycle. So we really think that this is the construction that we want to prove. Okay, and now how to prove such things. So the main idea is to use spectral properties of tournaments and tournament limits. So maybe some of you are familiar with graph limits. You can define a similar concept for tournaments. I will give a brief introduction in a moment. So we combine spectral approach and limit approach to be able to prove this theorem. So let me do a quick recap. What I mean by spectral approach. For every tournament, you can define an adjacency matrix, as always for graphs. So one whenever there is an edge between particular vertices. By tournament matrix, I mean the same, also adjacency matrix, but with additional terms equal to half on the main diagonal. Yeah, so it's basically adjacency matrix, but with those halves on the diagonal. Why we are adding those halves? This way, we have a matrix which is complementary. So if I sum up entries which are diagonal, in particular entry on the diagonal twice, then I get one. This is a nice property because all matrices with this property, they have nice spectral properties. I mean, if you take the eigenvalues, they are in particular, if one eigenvalue is in the spectrum of this matrix, then its complex conjugate also is in the spectrum with the same multiplicity. There is a real value in the spectrum called spectral radius, such that modules of every other eigenvalue is at most the spectral radius. Also, all real parts of the eigenvalues are non-negative and they sum up to exactly ½ And the thing that is probably most interesting for us in the setting of cycles is that if I want to calculate number of directed cycles of length L, then this is basically sum of ELF powers of eigenvalues multiplied by 2 to the power L. And so this way we, using the spectrum of this tournament matrix, can calculate the number of cycles in the tournament. Okay, but there are some error terms. And also we are interested in the limit because for small tournaments, you can have bigger number of cycles. I mean, bigger in terms of density. So we want to combine it with limit approach. And this way we can define a tournament limit. So tournament limit, let me start with what is a convergence sequence of tournaments. So if I consider a sequence of tournaments of increasing orders, I would be saying that it converges if for every tournament, like some fixed finite tournament, the density of this tournament in my sequence converges. Right? Density of one tournament in other tournament is just a number between 0 and 1. So we know when it converges. And we will say that the sequence of tournaments converges whenever this convergence happens for every tournament. Yeah, so this way we can define a limit object, and the limit object will be called tournamenton as an equivalence of graphon, and is a measurable function from a square to 0, 1, which satisfies the same property that we have from a tournament matrix. Yeah, so if I sum up the diagonal entries, I get 1. So what's the intuition behind it? So let me draw some tournamentons. By black, I mean value equal to 1. By white, I mean value equal to 0. So here I have a function which is, of course, I'm doing as in a matrix. So it's counting this way. And you can see that it resembles tournament matrix where every vertex is connected with everything from some moment to the end. And it, yeah, so it has forward edges, like first vertex to everything, second vertex to everything except the first one, etc. So it looks like a transitive tournament. Yeah, so intuitively speaking, this tournamenton is a limit of transitive tournaments. Similarly, if I take a function which is equal to half everywhere, then this is a limit of quasi-random tournaments. Yeah, while if I take a function which looks like this, so a vertex is, let's say first vertex is connected to everything in the first half by forward edges and then backward edges, and then everything is shifted. Yeah, so this is exactly this carousel tournament. Okay, so if we know something like this, what's the tournament, and we can prove the same properties as we have for graph limits. I mean, we can define what's the density of a fixed tournament in a tournamenton. It's just the probability that if I pick some random vertices, then the density of this tournament is basically a probability that those random vertices creates tournament T. By creates, I mean that we look for edge probability given by the value of the tournamenton. Yeah, and if we know what's the density of a tournament in a tournamenton, we can say that tournamenton is a limit of convergent sequence of tournaments if for every fixed tournament T, the density of T in the sequence, which we know that it converges to some number, it's exactly the density of T in the tournamenton. Yeah, and one can prove that for every sequence, converging sequence of tournaments, there is a limit tournamenton, and also for every tournamenton is a limit of a convergent sequence of tournaments. Yeah, so this is exactly the same as for graph limits, if you're familiar with the concept. The only difference between tournament limits and graph limits is in spectral properties. And why it's so different, the problem is that if we look at the tournamenton or a graphon as a linear operator, then in case of graphons, the graphon is symmetric. And the linear operator, which is coming from the graphon, it's self-adjoint, so it's really nice properties. It has real eigenvalues and everything is nice. For tournaments, we don't have this symmetric property. We have only that the diagonal entries sum up to 1. So it's something different. So it's not self-adjoint, and we don't know if the density of cycles of length L is anyhow related with the trace of this tournament to the tournamenton to the power L. And also, if we consider spectra of tournaments that are converging to the tournamenton, we don't know that they converge to a spectrum of a limit tournamenton. All the proofs for graph limit are using this symmetricity and spectral properties coming from it. And here we cannot do anything like this. So what we proved, we didn't prove exactly what we would like to. I mean that this tournamenton behaves nice, but we proved that if we consider a sequence of step approximations, so some specific particular approximation of our tournamenton, and we look at the spectrum of these tournaments and the step approximations, then they behave nice. Sorry. So we have a sequence of those step approximations of our tournamenton. We calculate the spectrum of each of them, and we look at the limiting multiset of those spectra. And what we obtain, it occurs that it satisfies the nice properties that we want. So multiplicity of each eigenvalue is finite except 0. If one eigenvalue appears in this limiting multiset, then also its complex conjugate appear there with the same multiplicity as it was for the tournaments. And if there is anything non-zero in the limit, then there needs to be a real value that is upper bounding the modulus of all the other elements of this limiting multiset. And most important fact for us, one more thing, all the real parts sum up, they are non-negative as it was for tournaments, and they sum up to something which is at most half. And the most important thing for us, so if we want to calculate the density of cycles in the tournamentum, then it's really equal basically to the sum of powers in this limiting multiset. So we don't know if it holds for trace of a tournament to specific powers, but if we consider this limit of spectra of step tournament approximations, then we have this property. So if we want to calculate the number of cycles in a tournamentum, we just need to calculate the sum of powers of eigenvalues, or not eigenvalues, those values appearing in limiting multiset of step approximations. Okay, so when we build this theory, now and we come to our proof, then the proofs are really short and easy. So let me do the first proof, so the conjecture of Bartley and Day, that if I take L, which is not divisible by 4, then really the maximum density of cycles is the same as in a random tournament. So firstly, we will also show when the maximum is achieved. When L is odd, we want to show that it appears on for any regular tournamentum. So if you take any sequence of regular tournaments, then you will have the maximum number of L cycles. While if L is even, and of course not divisible by 4, then the maximum is attained only in the random tournament. Yeah, so only if you consider sequence of quasi-random tournaments. Okay, and how to prove it? So firstly, you can prove some easy bound for complex numbers. If module of your complex number, which has non-negative real value, is bounded, then such inequality holds. This is easy to be proven, it's just by checking. And with such inequality, what we can do, we want to bound the sum of L powers. Sum of L powers is exactly the same as sum of L powers of real parts, because we prove that they come in pairs. So if you have an eigenvalue and its complex conjugate, they sum up to the same as sum of the real parts. Then we can use the above inequality so we keep the spectral radius, and for all the others we use the inequality. And now this is just sum of real parts power L, and since the sum of real parts is at most half, we get that this is at most half to the power L, and this is exactly what we wanted to prove, right? 2 to the power L times sum of L powers is at most 1. And now the question where the maximum is achieved. So if L is odd, then this first inequality holds whenever a real part of complex number equals to 0, which means that we need to have half in this limiting multiset, yeah, to have this inequality to be true, to be tight. And this is enough for us, which means that this limiting tournamentum needs to be regular. And this is exactly what we needed. On the other side, when L is even and not divisible by 4, this first inequality is tight only when Z is 0. So it means that half needs to be the only non-zero value in this limiting multiset. And it's the only non-zero value only when the tournamentum is equal to half almost everywhere. So it's really a limit of quasi-random tournaments. Yeah, so you can see that when the theory of tournamentons and its spectral properties is built, so now such a proof is just half a page. I can say it's a one-line proof if somebody writes it in a one line. Okay, The other proofs, I mean, for cycles divisible by 4, those upper bounds and 8 cycles, is basically the same idea, but a bit more computations and bounds on the complex numbers. So it's not interesting to be shown, but the main idea is the same. Okay, and what about forbidden cycle setting? So now I want to maximize number of cycles in an oriented graph, but not among all graphs, but when some other length of the cycle is forbidden. If we consider this for non-oriented graphs, this was considered earlier quite often. So let me just mention briefly a few results. It started already in the 80s by Erdős conjecture that was proved something like 10 years ago by 2 groups. And recently, Levitsky and Fender even proved the structure of extremal examples, that basically it's a blow up of a 5 cycle and nothing else for big enough n. Giori, Pach, and Shimonovi, already in the 90s, they proved that if I forbid a triangle and want to maximize some even cycle, then the best you can do is take a complete bipartite graph. And this can be generalized to forbidding other odd cycles. So if you want to maximize even cycle and you forbid odd cycle, then complete bipartite graph is the best that you can hope for. And recently with my PhD students, we generalized this Erdős pentagon conjecture to higher values of cycles that differ on length at most 2. In the harder setting, when this extremal number is not on the maximum order, Lior Grzesik, who was giving a talk yesterday, together with Asaf Shapira, they provided the order of magnitude for every forbidden cycle, CK, when we want to maximize something which is not a triangle, but a larger cycle. While for triangle, we have some bounds, but they depend on the Turan number of even cycles, which is not known in most of the cases. And those bounds were improved in recent years significantly. For C3 and C5, so it's a reverse problem than Erdős pentagon conjecture. We have a lower bounds by Bolobaj and Giori, and upper bounds were improved recently many times, but still there is a gap in the constant. We know the correct order of magnitude because extremal number of C4 is known. Okay, and as for exact results, Gerbner, Jerry, Metuku, and Wieser, they recently proved the value for maximizing C4 when you forbid some even cycle. And with my master student, we proved it for C5 and C7. So here we can have exact bound. Okay, but let me leave the non-oriented case. You can just see that it's considered quite heavily in recent years. For oriented setting, so we can define the same. So we define what's the maximum number of some particular oriented cycle of length L among all n vertex oriented graphs without specific cycle of length K. And together with Justyna Jaworska, Bartek Kielag, and Tomek Ślusarczyk, we proved that what's the order of magnitude in all cases. So the second case is easy when K is not divisible by L. So the forbidden cycle does not appear in the blow up of the cycle that we want to maximize. Then the maximum order can be achieved, of course, by taking a blow up of a cycle that we want to maximize. While in more interesting case, when we cannot take it just a blow of a CL, we prove that the maximum order of magnitude is just 1 power less, so n to power L minus 1. As a construction, we can take a blow up of CL, the cycle that we want to maximize, but with 1 blob equal to just a single vertex. Yeah, this way it's this order of magnitude, but we will not find any multiples L cycles. Okay, and just a quick sketch how to prove that this is really the maximum order of magnitude. So firstly, we remove edges that are appearing in some small number of cycles. This way we remove not much cycles. So we are keeping the same order of magnitude. And in the remaining graph, we can prove that there is no cycle of length, which is also a multiple of L, but a smaller one than the forbidden graph. It's something like multiple of size at most L minus 1 times the length of the cycle we want to maximize. With this, we can prove that there cannot be two vertices connected with two disjoint paths of length T. So any two such paths needs to share at least one middle vertex. And this gives this reduction of order of magnitude by 1 that we want to prove. And you cannot have such paths. And with this, you can just bound the number of those cycles that we are maximizing, CL, using the bound on the number of paths of length T. Yeah, so this is not hard to be proven. It's just building those forbidden cycles from pieces that we are forbidding. As for specific cycle length, so when we are maximizing triangles and forbidding C4 or C5, then it's quite easy. The best you can do is just a blow up of a direct triangle, a balanced blow up. For higher cycles forbidden, which are not multiples of 3, then it's the same construction, but there can be some small trashes inside. I mean, you can have some disjoint directed triangles inside one of the blobs. So the value will be slightly bigger, but it's a lower order difference. Well, for cycles, forbidden cycles, which are multiples of 3, we prove that if we forbid 6 cycles, then really this is the best construction. You really need to take 2 blobs of all but 1 vertex and 1 blob consisting of just a single vertex and connect everything as in a blow up of a directed triangle. For higher forbidden cycles, which are multiples of 3, we believe that it's the same construction, but we can have a bit more vertices here and you can have more trashes inside, which makes the proof a bit complicated and harder to achieve. For 4 cycles, Hull, Levitsky, Pfänder, and Boletz, they proved, but it's still unpublished, that if you forbid a directed triangle and want to maximize C4, then the best you can do is take a iterated construction of a C4. So we take 4 blobs forming a blow up of a C4, and then in each blob, we iterate this construction. So this gives the biggest number of C4 in the triangle-free setting. If we forbid other cycles not divisible by 4, then you can prove similarly as for triangles that the best you can do is blow up of a C4. But it's not the case that always you have those constructions only. For example, if you go for C5 without C3, already different constructions can appear. We prove that if you're maximizing C5 in a triangle-free setting, then the best is taking a blow up of a C4 with transitive tournament in every blob. So you can see that constructions are different, they are changing, and for higher cycles, there will be even more. For example, when we are maximizing C6, then a blow up of a C3 is far better than blow up of a C6. So there will be not the blow ups of the cycles that we want to maximize, but smaller blowups, sometimes with iterated constructions, sometimes with transitive, and the set of extremal constructions is bigger than we think. Okay, my time is running out, so let me finish here. Thank you for listening and enjoy the rest of the workshop.